Hello everyone, welcome back. This is the last video for this week. We will talk about linear regression. So we apply regression technique to examine the relationship between any type of independent variable and a quantitative dependent variable. Regression is a linear prediction model using one or more independent variables to predict the value of a dependent variable. A more complete name for multiple regression is ordinary least square multiple linear regression. Least square is the method used to estimate the regression equation. Ordinary is to distinguish the simplest methods of least square from more complicated methods, such as weighted least square and generalized least squares. Multiple means there are two or more independent variables. Linear describe the kind of equation that is estimated by the multiple regression method. So you often see various combinations of these terms, such as linear regression, least square regression, or OLS regression. The symbol will start from simple linear regression. We'll go through this very quickly. So the relationship between independent variable like education and dependent variable internet hours is not perfectly linear. Although some individuals' points lie very close to the line, none fall exactly on the line. In the real world, we are not able to come up with a linear equation that allows us to predict y from x with perfect accuracy. We are more likely to find a relationship approximating linearity, creating a line of best fit. So mathematically, the line is described with an equation for a straight line. This side is super important. It is a mathematical basic for learning linear regression. So the requirement is to remember the meaning of these letters. Y is equals to A plus B times X. Y is the predicted score of the dependent variable. X is the score on the independent variable. A is a y-intercept, or the point where the line across the y-axis. Therefore, A is the value of y when x is equal to 0. And B is the slope of the regression line. It is the regression coefficient, or the change in y that is associated with a unit change in x. Regression coefficient, B, is a measure of how strongly each independent variable predicts the dependent variable. So for each of these four lines in this figure, as x go up by 1 unit, what does y do? For equation y equals to 6 minus 2x, b is equal to negative 2, which indicate for each unit increase in x, y decreases by 2 units. There's a negative relationship between x and predicted y. For equation y equals to 2 plus 0.5x, b is equal to positive 0.5 here, which indicate for each unit increase in x, y increases by 0.5 unit. So we'll talk about what is multiple regression. You will pause the video and read the definition by yourself, which I just mentioned at the very beginning of this video. A more general way of writing an equation with two independent variables is y equals to a plus b1 x1, b2 x2, b3 x3. A linear equation is perhaps the simplest way to describe a relationship between two or more variables and still get reasonable, accurate predictions. Even if the true relationship is not linear, a linear equation will often provide a good approximation. When you do not know the true form of a relationship, start with something simple. So it's easy to modify the linear equation to represent certain kinds of non-linearity. For example, we include both age and the square of age in the equation to predict income. The two-variable linear equation is y equals to a plus bx. In most applications of regression analysis, the linear regression has more than one independent variable. For prediction purposes, you can usually get better predictions if you base them on more than one piece of information. For causal analysis, you want to be able to look at the effect of one variable while controlling for other variables. This is accomplished by putting the other variables in the regression equation. For example, a linear equation that predicts income with one independent variable, schooling. The equation is income equals to 8,000, the intercept, plus 1,000 times schooling. 1,000 here is the coefficient, the scope of the straight line. Next, we want to add one more independent variable, age, as a predictor of income. The equation is as income equal to 6,000 plus 800 times schooling plus 400 times age. The intercept and coefficient of schooling have changed by adding one more variable, age. This equation tells us that income goes up by $400 for each additional year of age. It also goes up by $800 for each additional year of schooling. For a person who is 40 years old and 14 years of schooling, the predicted income is $33,200. A more general way of writing an equation with two independent variables is we multiply each variable by the slope coefficient of that variable. We add these products together. Finally, we add the intercept. In our example, x1 is schooling and x2 is age. We still call it linear equation, although it's more difficult to draw a graph that looks like a straight line. It would have to be a three-dimensional graph, and the equation would be represented by a plane rather than a line. So this is the more detailed information of multiple regression formula. I would encourage you to pause for like 2 minutes and then read this detailed information of each element. Okay, so what kinds of variables can be used in multiple regression? This is not the knowledge you are going to read for academic paper, but you may use it afterwards when you have your own data. So interval ratio variables are good for multiple regression. Ordinal variables are also good for multiple regression. Strictly, ordinal variables are inappropriate for multiple regression because of a linear equation, but in practice, ordinal variables are often used in regression. And nominal variables, like dummy variables, are perfectly okay as independent variables in a multiple regression. So this is something you may use afterwards where you can memorize them. Okay, more practically, I will show some examples to walk you through how you rate the table and statistical results from academic papers. So for these slides till the end is very important. I encourage you to read them again and again. Okay, look at this example. On the left hand, you will see the gray letter. That's the sample where this table is from. You can download it from Quackers from this week. Okay, you may pause the video and take a look about the table first, and then we will discuss it. Okay, let's look at the estimated regression coefficient for education is 0.076. So the interpretation is with each additional year of education, self-reported health goes up on average by 0.076 points. It's important to remember the estimate of 0.076 controls for sex, race, age, and marital status. The variable education has a statistically significant coefficient. You can see it's marked 3-star here. So signal a coefficient whose p-value is less than 0.001. Next part, for a dummy variable, which takes two values for sex, like male is equal to 1, female is equal to 0. You can find this information in the paper. Usually good papers will introduce how they recoded their variable into dummy variable. So the only way to get a 1 unit increase is to go from 0 to 1. It implies the coefficient can be interpreted as the average value of the dependent variable for all the people with a value of 1 on the dummy variable minus the average value of the dependent variable for all the people with a 0 on the dummy variable, while controlling for the other variables in the model. For this reason, such coefficients are sometimes described as adjusted differences in means. In this table, male is coded as 1 versus not males. White is coded as 1 versus non-whites as 0. Married status is coded as 1 versus other, like single, of 0. Males have self-rated health that average 0.114 points higher than females. Whites have self-rated health that is about 0.239 points higher than non-whites, and married people have self-rated health that is 0.105 points higher than that of single people. So here your dependent variable is self-rated health. This table is from the article published by Rose and Wu 1995. Again, it's available on Quackers. So this paper aims to answer the question whether more educated people tend to be in better health than less educated people. If so, what are the reasons? This table presents the multiple regression results from the survey of 2,000 adults in the US. In this table, we see results from estimating two different regression equations. For both equations, the dependent variable self-rated health is a respondent's subjective assessment of their general health, coded as 1 very poor, 2 poor, 3 satisfactory, 4 is good, and 5 very good. The differences between these two equations is a number of variables in the regression. Equation 1 has 5 independent variables. Education is a number of years of schooling. Equation 1 also controls for 4 demographic variables. 3 of them are dummy variable. Sex is coded as 1 for males and 0 for females. Race is coded as 1 for whites and 0 for non-whites. Marital status is coded as 1 for married and 0 for others. The last demographic variable, age, is measured in years. To compare, equation 2 has additional variables, work, and economic conditions. For each equation, 2 columns of the numbers are presented, one labeled B and the other labeled beta. In the original table, you can tell from the footnote of the table, B is an unstandard regression coefficient with standard error in the parentheses. The beta column contains standardized coefficient. Beta is measured by standard deviation. For example, a change of 1 standard deviation in the independent variable will result in a change of 2 standard deviation in the dependent variable. So let's see equation 1. The estimated regression coefficient for education is 0.076. We can interpret the number like this. With each additional year of education, self-reported health goes up on average by 0.076. So I already repeated this explanation at the very beginning, but I want to repeat again to emphasize your understanding. So with each additional year of education, self-reported health goes up on average by 0.076 points. It's important to remember that the estimate of 0.076 controls for sex, race, age, and marital status. It tells us what happens when education changes, but all the other variables remain the same. Each of the coefficients represent the effect of that variable, controlling for all the other variables. We also have dummy variable, right? In the equation coded as 1 or 0. Again, I want to repeat some of them. So for example, the marital status, marital is coded as 1. Married people have self-rated house, that is 0.105 points higher than that of single people, because single is coded as 0, right? And 0.105 is higher than 0. So it means married is coded as 1 and single is coded as 0. So married people here, the B is 0.105. So married people have self-rated house that is 0.105 points higher than that of single people. Sorry about the complicated number to say, but that's the facts. That's the number from the paper. So the coefficient is interpreted as the average value of the dependent variable for all the people with a value of 1 on the dummy variable minus the average value of the dependent variable for all the people with on the dummy variable. So controlling for other variables in the model. Okay, we'll move to the next one. You may also ask, is a coefficient a large or small number? One way to answer that question is to determine whether or not the coefficient is statistically significant. You also notice many of the numbers have stars. We just mentioned like 3 stars. That shows p-value is smaller than 0.001. This is a common way to show which coefficients are significantly different from 0, and this is a practical technique you will use to read academic papers. The common way is as follows. A single star indicates a coefficient whose p-value is less than 0.05. 2 star means a coefficient whose p-value is less than 0.01. And 3 stars means the p-value is less than 0.001. So education's coefficient has 3 stars in both equation. All the variables in equation 1 have statistically significant coefficient. In equation 2, all the coefficients are significant except for sex. You see no stars for the B or beta for the role of sex variable. And also for marital status, no stars. And household income and employment part-time, no stars. So let's move to equation 2. It adds more variables that describe work status and economy status. So take employment status variable as an example. It includes 4 categories: employed full-time, part-time, unable to work, and not employed. You will find this information in the article, but not for this table. And therefore, we choose one category with a relatively larger number of people as the reference and leave out of the model. In this case, the category is not employed. 3 dummy variables are put in the model 2 to describe the work status. Each of them is coded as 1 or 0, depending on whether or not the person is in that particular status or not. So if the participant is in the employment full-time, that participant, it will be coded as 1. It's important to remember that each of these coefficients is a comparison between an included category and the reference category. For example, those employed full-time average 0.174 points higher in self-rated health, that's your dependent variable, than those who are unemployed. Those unable to work have a self-rated health is 0.835 points lower on average than those who are unemployed. Why lower? Because the sign for 0.835 is minus, it's not positive. So let's compare the 2 equations one more time. You may notice coefficient for education changed when we control for work and economic conditions from equation 1 to 2. It's decreased from 0.076 to 0.041 when other variables are introduced into the equation 2. What does it tell us? It tells us that the work and economic conditions variables play a very important role in mediating the impact of education on self-rated health. So let's talk about beta, the standard coefficient. If I want to compare, for example, a 1 unit increase on the economic hardship scale with a change from unmarried to married. I cannot do it because unstandardized coefficient B depend greatly on the unit of measurement for their unique variables. In this case, standardized coefficient beta solve the problem by putting everything into a common metric. Standard deviation units. For example, in equation 1, an increase of 1 standard deviation in education led to an increase of 0.22 standard deviation in self-reported health, row 1. Let's see, please check row 1. So an increase of 1 standard deviation in education lead to an increase of the 0.22 standard deviation in our dependent variable self-rated health. We can compare standardized coefficient across different variables. In this case, we can decide which variables are more or less important. In both equations, we see that age has the largest standardized coefficient, minus 0.247. Regardless of the sign, of course, marital status has the smallest effect in both equations with beta value of 0.058. So please remember, we want the largest absolute value, regardless of the sign, to have the largest effect. Okay, the constant doesn't tell us much from the table. We just need them as a baseline in the equation. So you don't have to interpret constant when you read academic papers. R squared, this is important information, tell us how well we can predict the dependent variable, knowing only the independent variable in the model. So with information only the independent variable in this model, how well we can predict the dependent variable. R squared is only 1.152 in equation 1 and raises increase to 0.234 in equation 2. Therefore, even though nearly all these variables have coefficients that are statistically significant, they account for only a small portion of the variation. Take-home message, R squared will always increase as variables are added to the model. The more variable you add to the model, the higher score you will get for R squared. It is true, the higher the better. However, there's no reason to reject a model if the R squared is small. For example, in equation 1, R squared is small, but we can still confirm that education affects self-rated health. In real world, a model with a high R squared could be a terrible model. So the reasons could be you put the wrong variables in the model or some assumptions are violated. Okay, the last slide is an example from my own paper published in the American Journal of Health Promotion. The present study examined the extent to which matched weight and weight perceptions predict adolescents' self-rated health, mental health, and life satisfaction. So table 3 represents OLS regression model of self-rated health, mental health, life satisfaction, weight and weight perceptions. So you will see 3 totally different models because we have 3 different dependent variables, or you will see 3 outcomes in this table. It is okay to have more than 1 dependent variable for your study. There's no problem. It's just you run them separately. So let's interpret some results here. In model 1A, the reference group is normal weight. For underweight boys, we do not see stars for B of 0.099. It does not indicate a statistically significant relationship. The interpretation is that the levels of self-rated health do not differ between underweight and normal weight boys because the p-value is larger than 0.05. It does not indicate a statistically significant relationship. Remember, we compare the reference group with the group you are interpreting. In contrast, compare with the reference group normal weight, overweight boys are associated with poor rated health. Why? Because we see the sign is negative. Negative relationship between the overweight boys and self-rated health. In addition, you can see 3 stars shows statistically significance of the relationship. We see the p-value is smaller than 0.001. We see 3 stars. The purpose of showing this table is to offer examples of presenting regression results in the table. So when you read academic papers, I hope you can have more knowledge of how to interpret the results from the table. Okay, so this is the end of the whole week, and I encourage you to watch this part, how to read academic paper again. So if you have any questions, feel free to let me know. And good luck for your week 7.